Welcome to this deep dive, where we unpack a fascinating piece of machine learning research. Today, we're looking at a recent academic paper. It's tackling a pretty big challenge in cloud security. How to automatically create access control policies using large language models.
Right, LLMs for security policies, it's a hot topic.
Exactly. And think about it, in these really complex cloud setups like AWS, writing these security rules by hand, it's not just slow.
Oh, it's incredibly error-prone, seriously easy to get wrong.
Which can lead to, well, major vulnerabilities. So this paper asks, can the AI that writes stories and code also write these vital security policies based on instructions?
Yeah, and the complexity is just staggering when you think about it. Who can do what on which resource under specific conditions?
Right.
Multiply that across a huge cloud deployment. The management effort is huge, and the risk of someone making a mistake just, skyrockets.
So this research is exploring a potential way out, using AI to automate it.
Precisely. Can LLMs take a description of what access you want and then synthesize a policy that actually correctly implements it? They looked at two main ways to give these descriptions.
Okay, what were they?
First, really clear lists. This request is allowed, that one's denied. Very concrete.
Makes sense.
And second, just using plain English natural language descriptions.
And as we'll get into, their early findings really seem to point to something crucial about using these AI models.
Yeah.
The clearer and more structured your instructions are, the better the results you get. Precision in the prompt seems absolutely key for getting accurate security policies.
That definitely tracks with a lot of LLM research. Input matters a lot.
So let's dig into the paper itself.
All right, so the paper kicks off by framing the problem, hammering home that manual policy creation is complex, it's error-prone, standard stuff, but important context.
Right.
Then they propose using LLMs, but with a specific angle, what they call a verification-based approach.
Verification-based, so not just generating and hoping for the best.
Exactly. It's about building in checks. Can we actually verify if the policy the LLM creates does what it's supposed to?
Okay, that sounds critical for security.
Definitely. And they set up three main research questions. First, can LLMs make accurate policies from those simple allow-deny lists?
The concrete examples.
Right. Second, how well do they do with just natural language descriptions? The way a person might describe it.
Which sounds harder, more ambiguous.
Potentially, yeah. And third, crucially, does giving them more structured prompts, something more formal than natural language, actually lead to better, more accurate policies?
Got it. So the paper lays out how they tested these questions.
Yep. Methodology, experiments, results, the whole academic structure.
Now, this idea, automating security policy creation, it's not completely out of the blue in machine learning, is it? What came before this?
That's a great point. It builds on earlier work. There's been research into tools to help create policies, but often they weren't fully automated or lacked strong guarantees, the kind of verification they're aiming for here.
Like what kind of tools?
Well, things like policy mining, trying to learn rules by watching access patterns. More reactive, really.
Okay.
Then you have constraint-based methods. AWS's Zelkova is a good example. Great for analyzing existing policies, checking compliance.
So analysis, not generation.
Mostly, yeah. Though there's work on repair, too. This paper leans heavily on that formal verification idea, using SMT, Satisfiability Modulo Theories.
SMT, right? That's the mathematical logic approach.
Exactly. It lets you formally prove things about the policy, not just test it. They also mention other recent work using LLMs as coding assistants for security software, so it fits in that broader trend.
Okay. For listeners maybe not deep in AWS policy details, could you quickly break down what makes up one of these policies?
Sure. Basically, it connects a principal who's asking. Could be a user, a group, an application.
Okay.
An action. What are they trying to do? Like read a file, launch a server, delete something.
Got it.
And a resource. What are they trying to do it to? A specific file, a database, a whole category of servers. And often there are conditions like only allow if they're connecting from the office network or only during work hours.
Principal, action, resource, condition, PARC.
Sort of, yeah. And the logic is usually access is granted if there's an allow rule that matches, and there's no deny rule that explicitly blocks it. Deny usually wins.
Okay. Deny takes precedence.
Typically. And what's cool here is how they encode these policies into those SMT formulas. It turns policy checking into a math problem.
How does that help?
Well, you can check if a formula is satisfiable, basically. Does a situation exist where this rule applies? That tells you if a request would be allowed or denied. And you can compare policies mathematically. Are they identical? Is one more permissive, allowing more access than the other?
That sounds powerful for comparing the LLM's output to what was intended.
Exactly. It's a rigorous way to evaluate correctness.
So how did they actually test the LLMs? What data did they feed them?
Right. Finding good data is often tricky. They started with a data set called Quacky. It has 40 policies pulled from AWS user forums.
Real-world examples, then?
Yeah, people asking questions, sharing their configs. Then, to broaden the scope, cover more AWS services like S3, EC2, IAM, they synthesized 7 new policies themselves.
Okay, so 47 policies in total that they consider the ground truth, the correct versions.
Correct. These 47 were their baseline for comparison against what the LLMs generated.
And the prompts. You mentioned 3 different types they used to ask the LLM to create policies.
Exactly. Designed to hit those research questions. First was concrete requests.
The allowed nanny lists.
Yep, specific examples. Allow Alice get object on bucket edge of file.txt. Deny Bob put object ACL on bucket B. They varied the number of examples, the complexity.
Gotcha. What was the second type?
Coarse-grained. These were natural language descriptions written by engineers summarizing the intent of each ground truth policy, like Deb should have read access to all S3 buckets. More general, less precise.
More like how a manager might ask for something.
Kind of, yeah. And the third type was fine-grained with syntax.
That sounds more structured.
It was. They used a specific SQL-inspired syntax to define the requirements very precisely. Again, engineers crafted these for each ground truth policy. Something like allow principal, group.developers and AD action gets 3.doc any resource equals arn.s.s3, much less ambiguity.
Okay, 3 distinct ways of asking. Concrete examples, general English, and a structured language. So how did they measure if the LLM did a good job?
It depended on the prompt type. For the concrete request ones, they used that SMT encoding.
The math checks.
Right. They took each example request from the prompt and checked.
Yeah.
Did the LLM's policy classify it correctly as allowed or denied? Then they calculated correctness score percentage of requests classified right.
Like running it through a simulator.
Pretty much, yeah, analogous to AWS's own policy simulator. For the other 2 types, the natural language and the structured syntax prompts,
Yeah.
they compared the LLM's policy against the original ground truth policy using SMT solvers again, but this time looking at relative permissiveness.
So did they allow the same things?
Exactly. Did they allow the exact same set of requests? That's equivalence, the ideal outcome. Or was one policy strictly more permissive, allowing everything the other did plus more? Or were they just different, incomparable, allowing overlapping but distinct sets?
I see. Equivalence is the goal there.
That's what you're aiming for, yeah. Matching the intended behavior.
So the moment of truth. What did they find when they ran these tests using GPT-4? How did it do with these different prompts?
Okay, results time. With the concrete request, the specific examples GPT-4 actually did reasonably well. An average classification rate around 84%.
84%. Not bad, but not perfect either.
Right. It suggests that given clear examples, the LLM can often generate a policy that follows them. But they noted it struggled a bit more when there were lots of examples or a wider variety of actions and resources involved.
Okay, complexity hurts performance there.
Yeah.
What about the natural language prompts?
That's where things got, well, messy. For the coarse-grained natural language prompts, most of the generated policies were incomparable to the ground truth.
Incomparable, meaning they were just wrong.
Often, yes, or at least significantly different. The researchers found the LLM tended to create overly broad policies, too permissive, granting way more access than intended, likely because the natural language was just too vague.
The ambiguity problem. That makes sense.
Exactly. But then came the fine-grained, structured syntax prompts.
The SQL-like ones.
Yes. And here, the results were dramatically better, a significant improvement. The LLM produced much more precise policies, often equivalent or very close to the ground truth.
Wow, so structure really is king here.
It strongly suggests that, yeah. Clear, unambiguous, structured instructions are vital if you want LLMs to generate accurate access control policies. That was the big finding for RQ3.
So summarizing that, LLMs can do this, potentially, but how you ask them matters immensely. Concrete examples are okay-ish, natural language is risky, structured language works best.
That's a pretty good summary, yeah.
What does this mean for the real world? For cloud security folks, for sysadmins?
Well, the potential implications are pretty significant, I think. If this approach can be refined and made reliable,
Yeah.
it could seriously reduce human error in security configurations. We know that's a huge source of breaches.
Definitely.
It could save tons of time and effort for administrators, letting them focus on higher-level security strategy instead of fiddling with policy syntax.
Freeing them up.
Right, and potentially lead to more secure, more fine-grained control overall. Maybe even lower the barrier for smaller companies to manage complex permissions effectively.
But there have to be catches, right?
Yeah.
Challenges.
Oh, absolutely. Big ones. The verification piece is non-negotiable. You have to be able to trust these AI-generated policies. Robust checking is essential.
Can't just deploy it blindly.
No way. And related to that is user trust. Getting admins, getting organizations comfortable relying on AI for something this critical, that's a hurdle. You need high assurance it's doing exactly what's intended and nothing more.
Yeah, I can see that being a major adoption challenge.
Yeah.
Okay, this feels like a good point to transition to our novel notions segment. Based on this paper, what new research ideas or directions pop into your head?
Okay, novel notions. One idea that jumps out, building on their verification work, is maybe a self-refining policy synthesis engine.
Self-refining. How would that work?
Imagine the LLM generates an initial policy based on, say, a structured prompt, but then it doesn't stop. It automatically feeds that policy into a verification tool like the SMT solvers they used.
Yeah.
The tool checks the generated policy against the requirements, maybe against concrete examples too, if it finds mistakes, discrepancies.
If LLM fixes it.
Yeah, the system feeds that error information back to the LLM, which then iteratively refines the policy. It's like the LLM is debugging its own output.
Huh, like a feedback loop.
Exactly. You could even think about using reinforcement learning, where the reward is getting a verified correct policy. Given how well the structured prompts worked, they'd be crucial for guiding this refinement loop. It could lead to a system that gets better and better at generating accurate policies over time.
An AI that learns to write perfect security policies through trial, error, and verification. That's pretty cool. What else? Any other directions?
Another thought, maybe acknowledging the limitations, especially with natural language. Perhaps a hybrid human LLM policy co-creation framework.
Hybrid, so human and AI working together.
Right. Instead of full automation, think collaboration. A human admin provides the requirements, maybe using high-level natural language, because that's easy for humans.
Okay.
But the LLM's first job isn't to write the final policy, it's to translate that natural language into the structured, fine-grained specification language, like the SQL-ish syntax from the paper.
Ah, so the LLM creates the structured prompt for the natural language.
Precisely. Then, the human admin reviews that structured spec. They can understand it, check it, refine it using their expertise.
And making sure the translation captured the intent correctly.
Exactly. Once the human signs off on the structured spec, then the LLM generates the final executable policy from that precise input.
So you get the ease of natural language input, but the precision of the structured language for the actual generation. Best of both worlds.
That's the idea. The LLM could even act as an assistant during the review, maybe flagging ambiguities it found in the original request or potential security risks. And importantly, it could also generate natural language explanations of the final policy, making it easier for humans to audit and understand.
That sounds really practical, actually, combining human oversight with AI's translation and generation power.
Yeah, leveraging the strengths of both.
Yeah, some really thought-provoking ideas there. So wrapping up our deep dive on this paper, the main takeaway seems pretty clear.
Yeah.
LLMs definitely show promise for automating access control policy creation, something sorely needed in complex cloud environments.
Mm-hmm.
But the way you talk to these models, the input you give them, is absolutely critical.
Couldn't agree more. Structured, precise instructions seem essential for getting accurate, secure results. Just throwing natural language at it seems too risky right now, leads to overly permissive policies.
Yeah, the ambiguity is the killer there.
Exactly. And it really opens up exciting avenues for future work, doesn't it? Refining prompting, developing these specialized policy languages, exploring those hybrid human AI models. Lots to do.
It definitely highlights how AI is starting to intersect with core security practices. Gives you a lot to think about regarding the future of access management. As always, if you want to read the paper yourself, the link is in the show notes. Thanks for joining us for this deep dive.